So, hi everyone, my name is Krzysztof, and today I'll be giving a talk called Back to the Future with Platform Security. But before I begin, I just want to give out a shout to two of my colleagues, Enrica and Joseph, with whom I've done this research with. So, the outline for today's presentation is as follows. First, I'll give a small introduction into how the research started and the problems we ran into. Then I'll talk about protections, both classical and modern ones, that have been adopted in recent years. And for each of the protections, I'll present a couple of vulnerabilities. And as a cherry on top, I'll show you how we can combine these vulnerabilities to actually obtain persistence in firmware, basically by implementing a backdoor running in ring -2. And finally, I'll wrap up with a few conclusions. So the research began by just simply purchasing an Asus Ryzen laptop, and the first thing we did was just start fuzzing SMI handlers, and the system immediately hung, which we thought, well, great, right? That's already a good start. However, when we tried to dump the SPI flash to reverse the SMM modules and try to determine which one of these actually caused the crash, we weren't even able to do that with existing tooling, which led us to a series of basic questions that, while they are well researched on Intel-based platforms, on AMD, not so much. So these questions are, for example, which registers do we have to configure to protect SMRAM? Or, for instance, what about the SPI flash to prevent malicious access? And what about hardware secure boot, right? All these technologies, we know all about it on Intel, but AMD, So when we started looking into it, we found that the documentation was very scarce, and actually interesting technologies like AMD ROM armor or platform secure boot are under NDA, so you cannot really get your hands on those unless you're one of the OEMs. And when we tried to look if anybody else has actually looked into the topic, we haven't really found anything. So this leads us to the next disclaimer. All the discussed information here has been obtained through reverse engineering without access to documentation, or at least restricted documentation, and as such, there may be some inaccuracies in our conclusions. So, since today's presentation will be a roadmap into, a roller coaster into different AMD platform security technologies, I'd like to lay out a path that we're going to take so that we don't get lost. So we will assume that we have already successfully compromised the operating system, so we're running in ring 0, and what we want to achieve is persistence in ring -2. That's, in platform security, the holy grail. And as we can see from the simplified view, the two things that we need to do to get there are we need to have a primitive to actually write to the SPI flash what the firmware lives. And we also have to break hardware secure boot that verifies the firmware code. So let's begin. So first off, let's talk about the SMM configurations. So for those that aren't familiar with SMM, it stands for System Management Mode. It's highly privileged code that runs in ring -2, as opposed to the operating system running in ring 0. It's triggered via system management interrupts, and since SMM lives in a portion of memory called SMRAM, there must be a mechanism to protect actually manipulations of it from the operating system. So, as a small side note, in order to trigger SMIs, this actually is done a little bit differently compared to Intel, because we have a register that we can configure to say to which I/O port actually we need to write to trigger SMIs. On Intel, that's always been B2, but if suddenly, for example, your fuzzer doesn't work, then this might be because it's configurable. But typically, it's going to be I/O ports B0 or B2. So there are two mechanisms to protect SMRAM memory. ASEG and TSEG. ASEG is basically a legacy technique that is not used anymore, so the way to go is TSEG. And there are 4 registers that I use to enforce these protections. The second and third register, which are the TSEG base address register and the TSEG mask register, I used to define the base address, the size of the TSEG region, and whether the protection is enabled or disabled. Then we also have the SMM base register for defining the base address of the SMM code. And we also have the hardware control register, where we have one specific bit, the SMM log bit, that is used to lock down the previous registers. So we implemented all this logic into our in-house developed tool called Padbox, and we gave it a spin against different systems that we had on hand. And to our surprise, one of them was actually vulnerable, where we saw that the SMM log bit was not set. What does this mean to us? That basically from the operating system, by just manipulating one of the registers, the SMM mask register, we can disable TCP protections directly and thereby open up the TCP region and start manipulating, for example, SMM code. So privilege escalation in this case would be trivial. If you're interested in this topic and want to read a little bit more about it, I here provided a link to a blog post we wrote on the topic. So when we dug deeper into this SMM log, our understanding initially was that the SMM log bit can only be cleared upon a processor reset. But to our surprise, that was not quite the case. In fact, there is a register that can be used to clear the lock at runtime. And we were like, okay, what? Is this really true? So we kept on reading and we saw that the SMM key MSR can be configured at boot time before the lock is applied, so that at runtime you can actually clear the lock and afterwards, for example, manipulate the previous register so you can change TCP configurations as you wish. And while we thought long and hard about what the use case for this could possibly be, I mean, we couldn't find any proper answer except for, well, it's an architectural backdoor. Luckily, after skimming through the firmware of different vendors, we haven't found this being used in practice. But I'd still like you to keep this in mind, because actually we're going to use this technique, use this register later on for the demo. So one more protection that is related to SMM or SMM callout protections. And they basically prevent instruction fetches outside of SMRAM when the CPU is in SMM mode. And for those more familiar with like OS level protections, this is basically the equivalent to SMAP, but for SMM. So we found that, of course, Intel does implement this protection, and for that they use the MSR SMM feature control register to prevent instruction fetches outside of SMRAM. But for AMD, there was no equivalent protection. So we tested this on various systems, and we haven't found this protection at all, which means that SMM callout issues of any kind, like, for example, uninitialized function pointers or corrupted return addresses, these kinds of things, they are trivially exploitable, because simply the code will jump outside of SMM, and that's it. It's going to execute happily from there. And only in recent systems, specifically one from 2023, we saw that the vendor started implementing paging to actually mitigate this, but this was only the case for one of the systems we saw. So, going back to our roadmap, this is where we are. At this point, we have potentially compromised SMM via the misconfiguration issues, or maybe by exploiting some vulnerabilities. We're actually going to see some examples of that later on. And we want to attack the SPI flash. So, let's take a look at how the SPI flash is configured. So, on an architectural level, at runtime, access to the SPI flash should be only allowed from SMM and only to specific portions of the flash. And typically, this is where, like, the portion of the flash is typically going to be where UEFI variables live, which is kind of firmware configuration data, so to speak. And there are two ways to access the SPI flash. One is so-called direct mode via mapped.io, and the other one is indexed via programming the SPI controller. And for each of these methods, there is a corresponding protection that needs to be enforced. So, going to the first one, the ROM protected ranges. It basically protects accesses via memory mapped.io, and you define up to 4 ranges of up to 16 megs each. There are also separate registers that basically enable and disable these regions, and also there's a log bit to prevent manipulations from the OS. And these registers can be reprogrammed only from SMM when the log bit is set. When we were testing this feature, we actually found a couple of quirks that we cannot quite explain. For instance, we weren't able to write using this method to the SPI flash, neither from the operating system nor from SMM, which was really weird. And despite the enable bit not being set, the protection was still enforced. And this we tested with read access. So if any of you has any idea of what's going on here, or maybe at a future point in time, figure it out, just give us a shout. So once again, we implemented this into our tool just to understand, okay, how are these systems configured. And here we, for example, can see that on this one example, we see where the range starts, where it finishes, and whether there's a read or write protection applied. So the second protection is called SPI restricted commands. It applies to indexed access via SPI registers, and it defines which SPI operations are blocked. So you can define up to 8 SPI operations. Once again, there is a log bit to prevent the OS from manipulating all these registers, and you can reprogram all of that from SMM. And typically what's going to be blocked is the SPI write enable operation, because for those that are a bit more familiar with SPI, before a SPI write transaction, you always have to send a SPI write enable opcode before performing the actual write. So by blocking the SPI write enable operation, you block any writes to the SPI flash. And for reference, we also include how the relevant registers need to be configured. So going through the flow, how the SPI read happens using this method, it's relatively straightforward. We first program the opcode, so in this case 13 for reading, then the number of bytes that we want to send, the number of bytes we want to read, so x40, that's 64, the address from which we want to read, and afterwards we just trigger. And at this address, at hex84, we can see in green basically what's returned from the SPI. So again, we implemented a couple of checks into our tool, and we found that on one system, the Lenovo ThinkPad P16S, these registers were not configured at all. So we can see they are all zeros, so none of the SPI write operations would be blocked. And as such, we can basically manipulate directly from the operating system the SPI flash. When we tried to understand where this issue was coming from, like in which portion of the code, we found that this was in the AMD reference implementation. And this is important because when we take a look at the supply chain, we basically see that, for example, Intel and AMD, they provide reference implementations, and then IBVs, ODMs, and OEMs going down the chain, they can make their own adjustments. So the higher up in the chain you find the vulnerability, the more systems are going to be affected. So once again, we just try to put this to the test. So using the previous method, we just are going to try to write to the SPI flash on the Lenovo, and we just configure the previously mentioned fields in the SPI controller, and we want to write the value 41, and when we got to the corresponding memory, we see that the 41 was written. Great. So far we have seen that the security of the SPI flash relies largely on the security of SMM. If we manage to compromise SMM, we can compromise the flash. So when we dug deeper into SMM modules related to the SPI flash, we found a couple of interesting examples, one of which I want to present. So there were 2 modules that were actually exposing an interface to the operating system that was related to the SPI flash. One was called System Firmware Device SMM, the other one FVB Services Runtime Dixie, and both we found issues. For both we have CVEs, but in this presentation I just only want to focus on the second one. So first we stumbled into the Firmware Block Service SMM module, which is developed by Insight, so that's a little bit higher up the chain, and it affects different OEMs. And we saw that this module exposes an SMI handler with various SPI operations like read, write, and erase. Already in itself, this is a problem because we can manipulate portions of the SPI flash like that, right? So for example, we can change the values of UEFI variables, which, for instance, configure secure boot on your system. So from the operating system, we can just switch off secure boot permanently. But if we want to, for example, manipulate the firmware code, while we can do that, this should be still prevented by hardware secure boots, which should verify the firmware code, right? So when we took a peek at each of these operations and how they were implemented, we found that reads are typically done for performance reasons via memory mapped I/O by just simply making a mem copy from a certain memory region where the SPI flash is mapped, and writes are done via indexed mode. And the SPI read was particularly interesting since the SMI handler wasn't doing any kind of validation of the parameters. So here we can actually see the SPI read 0. We passed 3 parameters: the destination address, the source address, and the size. And under the hood, SPI read 0 is basically just a mem copy. So, well, we have a fully controlled mem copy pretty much, and we can start exploiting this thing like it's 1999. So right when we thought that we had gold, unfortunately, we found out that the interface is closed down at an early boot phase, and we weren't able to exploit this. But we didn't give up. We kept on digging, and we found actually a different SMM module, the FVB Services Runtime Dixie, that essentially works as a proxy and reopens the previous interface for us. So we're able to use it and abuse the previous issue. So to exploit the bug, we had to understand how the structure looks like that we have to pass to the handler. And this is done via a so-called communication buffer. In it, there are 3 fields which are really important to us, which are the source address, it's an arbitrary pointer, the size, which we fully control, and the destination buffer. But the destination buffer is not quite an arbitrary pointer, it's just the memory after the communication buffer itself. So while we don't fully control it, we can basically implicitly control it by moving the communication buffer to a different portion of memory. So with all that in mind, we get an arbitrary read like this by just simply pointing the source pointer to the beginning of the TSIG region, and we can copy all of SMRAM. So we can get a nice dump for later exploitation or analysis. And we can also get a write primitive with this. So this is really no rocket science. It's straightforward. So you might wonder, okay, so what do we write to TSEG in this case? Well, we can just simply take the previous dump. We can make some manipulations of that to change maybe some portions of the code, to inject something, and then just simply using the write to write the memory back. And that's it. So if you're interested in the exploits, we actually published this on our GitHub, so go ahead, play around. And also SMRAM dumps if you want to analyze maybe some SMI handlers or so. It's all publicly available. So going back to our roadmap, we successfully managed to compromise SMM, both using configuration issues as well as vulnerabilities in the code. We compromised the SPI, both via SMM and from the operating system. But there is one technology that I've omitted that AMD provides to try to mitigate this issue, and that is AMD ROM armor. So essentially, it's AMD's equivalent of Intel's protected range registers, and what they try to prevent with that is basically attacks from SMM. And when this technology is enabled, the host CPU is no longer allowed to make SPI write transactions. So every time that the host wants to make a SPI write, it must go for the so-called PSP. And to visualize this, let's take a look at the following diagram. So the host CPU, neither from the operating system nor from SMM, can talk to the SPI flash anymore, and instead it has to talk to the platform security processor, which is a chip embedded in the AMD SoC. So the PSP holds a whitelist of regions that the host CPU can write to, and every time it gets a request to write to the SPI flash, it's going to act as a gatekeeper and either say yes or no. So the whitelisted regions that the host CPU can now access are defined by the OEM and are embedded at build time into the firmware, specifically the PSP directory. And the PSP directory is simply a data structure within your firmware image. Now, normally, what should be whitelisted is just the NVRAM region where UEFI variables live, so that we cannot, for example, try to write to the firmware code. We created a script to parse this, and the script will simply take a firmware dump. It will parse the PSP directory, extract the whitelisted regions, and display them nicely like this. So here in this example, we see an Acer Secure Core PC, where we just plug in a firmware dump, and we get exactly the regions that are whitelisted. And if you compare like these addresses that the tool extracts and the SPI flash, you'll see that in this case, indeed, that corresponds to the NVRAM region and the SPI flash. So next, we reversed an SMM module responsible for communicating with the PSP for ROM armor-related commands. And we found that the flow is relatively simple. Essentially, 4 things happen. First of all, an enforce SMM only mode command is into the PSP, so that only SMM can actually trigger SPI transactions. And then some SMM-related information is into the PSP as well. And then 2 interfaces are registered. The first one is an interface for other SMM modules, so they can also talk to the SPI, so not that interesting to us. But there is also one more, which is exposed to Dixie drivers at boot time. So after reversing the previous SMM modules, we understood that the communication actually happens via a mailbox and doorbell mechanism. We also understood the message structure that we have to send to the PSP to talk to it. And at this point, we thought, well, what is it that actually prevents us from the operating system sending a message to the PSP, ringing at the doorbell, and communicating with it directly? So the trick lies in how SMM-only mode is enforced. So first, when the module is initialized at boot time, it sends a command to the PSP to say, okay, SMM-only mode is active. And the way this works is essentially when a SPI transaction, when the host wants to basically from SMM write to the SPI flash, it's first going to set a special flag that lives in SMRAM, and then it's going to notify the PSP, hey, I want to make a SPI write transaction. And then afterwards, the PSP, when it receives the request, it's going to check whether the flag was set, and then only go ahead with the transaction if the flag is the value that it expects. And that's it. So going back to the SMI handler we marked as red before, essentially it just provides an interface so that at boot time, Dixie drivers can also talk to the SPI flash, and it exposes these typical functions just like before, SPI read, write, erase, but also a deregistration of the SMI handler so that nobody later on can talk to it. And it has plenty of issues with unchecked pointers, once again, just as messy as in the previous example, and we can exploit these issues potentially in the same way. However, the issue actually lies more in the fact at which point in time this interface is deregistered. And to understand this problem, we need to take a step back and take a look at the UEFI boot process. So first we see that it's divided in different phases like sec, PI, Dixie, etc. And the initial phases are the most important ones, like sec, Dixie, sec, PI, and Dixie, because this is where most of the platform configuration is applied, and also this code is developed by the OEM. Anything that runs after the Dixie phase, platform security features should already be fully configured, so we cannot manipulate them anymore. And that code is developed by third parties. So at that point in time, what's going to be running is, for instance, a Linux or Windows bootloader. And going back to our Dixie driver, what happens is the interface is actually deregistered too late, specifically when a special call is made, which is called exit boot services. And that function is just simply called write when the bootloader hands over control to the operating system, so between TSL and RT, pretty much. Which means that there is a point in time after Dixie where this interface with all these bugs is still available, and potentially vulnerable third-party developed code is running. Like, for example, On Linux, there would be the grub bootloader. So we saw some issues in that in recent years, like the bootfall vulnerability. And same goes for the Windows bootloader with the Black Lotus vulnerability. So similarly to before, to the previous issue, we found that this is an AMD reference code, and it applies to quite a few systems. So, all right. So at this point, we have basically obtained a primitive to compromise the SPI flash. And in order to obtain persistence, we still need to break hardware secure boot, which brings us to the next topic, AMD platform secure boot. But before we dive into it, I just want to emphasize one thing, which is that firmware implants, they live in early UEFI boot stages, because this is where the most privileged code on the system runs, and because not all of the platform security configurations are applied yet. Once the handover to later boot stages is done, we don't really have full access to the platform anymore. So platform secure boot is implemented using the PSP, which functions as the hardware of trust. And for some reason, it's an ARM chip embedded within the AMD SoC. And what it does is it verifies the first two phases of the boot process, which are SEC and PEI. And later on, a vendor-specific PEI module is going to verify the Dixie phase. So to visualize this, the PSP will verify second PEI. And afterwards, a vendor-specific PEI module will verify the Dixie phase. And afterwards, the all too familiar Windows or Linux bootloader is going to run. So diving in a little bit more detail, the trust hierarchy looks as follows. The PSP, what it's actually going to verify, is going to be first the AMD root signing key. And afterwards, the root signing key is going to be used to verify the BIOS signing key. And the BIOS signing key is going to be used to verify the BIOS PEI firmware volume, where the SEC and PEI code lives. And then afterwards, the OEM-specific PEI module is going to verify the Dixie firmware volume. So at this point, we understood, okay, the high-level architecture of the system. We understood the trust hierarchy. But we also wanted to know how we can determine whether the system is properly configured. So for that, we found one PEI module that actually interfaces with the PSP. And it does so to actually check the state and potentially automatically configure the feature. This is done in two steps. First, the module determines the MMIO base address of the PSP. And afterwards, from that base address, it navigates to an offset where certain registers live. And there are two which are relevant. The first one is the PSB fuse register and the PSB status register. Luckily for us, this PEI module, the vendor left in this PEI module debug strings so that we knew exactly how the structure of the registers looks like, and reversing was just simply a piece of cake. So to visualize this once again, there are many different fields in the first register and the fuse register, but the ones that I want you to focus on are the PSB enable field and the customer keylog. And basically what we know is when the PSB enable bit is set, we know that PSB is enabled. And it also has to be locked down, because until that point, actually the fuse is not burned and manipulation is still possible. So these two values have to be set to 1. Then we also have the status register. And here we know that if PSB is enabled, then the status after the system boots, it has to return 00. If it returns a non-00 value, then we know that something went wrong. So on a properly configured system like the ThinkPad P16S, we see that the fuse register is properly configured, everything fine. We see that the PSB enable bit is set to 1, customer keylog as well, and that the status field also returns 00. So everything great. Then we also found systems that are not so well configured, like the Acer Swift, where we see that the fuses are not configured at all, and that the PSB status field returns 01, meaning something went wrong. So at this point, we had to put all of this to test, right? I mean, we have all these primitives to write to the SPI flash. We know that some of these systems are misconfigured, so that actually the codes that we can potentially manipulate shouldn't be verified at all. So yeah, time to get our hands dirty. So to be more precise, we didn't write just one exploit. We actually wrote two. The first exploit injects a backdoor into the firmware using the previously mentioned SPI flash write vulnerability, and also another exploit that is going to use the backdoor to disable certain protections. So first, at boot time, the backdoor will configure the SMM key register that I mentioned before. And then at runtime, when we run the second exploit, we're just going to disable TSIG protections and be able to exploit SMM. So let's take a look at this thing. So on a clean system, let's see. On a clean system, we first run the test to just demonstrate that, oops, let's go back. We first run the exploit to demonstrate that configuring the SMM key will not do anything, so we configure it, boom, and it still returns FFs, so the protection was still in place. But then afterwards, we use the other exploit to inject into the firmware the backdoor. And basically using the SPI flash write vulnerability that we had before, we just manipulate the firmware image with a malicious Dixie driver that at boot time will configure the SMM key. Then we reboot the system and see if it worked. So here it's just writing to the SPI flash, nothing special really happens. And since this takes a little while, about 1.5 to 2 minutes to write to the SPI flash, I'm just going to skip over it because there's really nothing to see. So when he's done, he'll just notify, hey, done patching, and then we reset the system and see if the backdoor worked. So then he goes into reset, and we try to run the previous exploit again. So we read the TSIG, from the TSIG region to see whether the protections are still applied. Yes, so we didn't do anything shady so far. Then what we do is we input the SMM key that we configured at boot time. We disable TSIG protections. And afterwards, here we see, once we've done that, we can actually access the TSIG region. And basically, at this point, from the operating system, we have full read and write access to SMM code. So approach escalation is trivial. And we know that the backdoor worked. So going back to the roadmap, to summarize what we've accomplished, we managed to escalate privileges to SMM. We managed to compromise the SPI flash. And we managed to find a misconfiguration in platform secure boot to obtain persistence. And I want you to take a step back and think about the impact, because from the operating system, there is no way to detect firmware implants. And it bypasses any protections that could be applied from the operating system or from the hypervisor. And firmware updates can also be blocked by the implant. So updates, well, basically the only way that you can detect whether this is running on your system and maybe try to remediate this issue would be just to simply pop open your machine, take a SPI programmer, dump your SPI flash, and manually inspect if you have anything on your system. So pretty bad. But it gets even worse. And this is because we can actually permanently disable platform secure boot. In fact, there is a combination of registers. We can burn them if platform secure boot is not configured. We, as the attacker, can actually burn them to prevent anybody ever enabling in the future platform secure boot. And this actually reminded us of a talk by Alexander Ermolov on Intel BootGuard, where basically the same thing was possible, where he not only was able to permanently disable BootGuard, he was also able to even configure BootGuard, so it only allows running firmware signed with the attacker's key. So then we went ahead, notified the vendors, and we received some very interesting responses. Starting with Acer, they considered that secure boot and some secure flash technology would protect them from attackers, but as we just saw in the demo, that's not quite the case. Lenovo said that basically none of their laptops up until 2022 were designed with this feature in mind, so none of the laptops up until 2022 have platform secure boot enabled on Lenovo. And considering that Lenovo also has laptops for enterprises, especially like the ThinkPad P16s, we thought, well, that's actually a good candidate for an AMD-based laptop that maybe companies buy for their employees, but it also wasn't, well, on that one actually it was configured, but on other ones, also from 2022, that was simply not the case. And then for Huawei, we saw that, that basically on their most recent AMD-based model, the Huawei MateBook 16S, the feature wasn't enabled, and they said they don't even have a plan to patch this. And on top of that, they even asked us not to publish any information because it might confuse users. Great, right? So yeah, now that we covered configuration issues, I also wanted to make to look into potential implementation issues. And just to quickly recap, we know that the PSP verifies second PEI. We know that second PEI verifies Dixie. So what we wanted to focus on is actually the second part of the trust chain to avoid reverse engineering all the PSP firmware. So as our test case, we actually took a look at the Lenovo ThinkPad P16S because it was one of the very few systems actually that had platform secure boot enabled. And based on previous research, we knew that they use a Phoenix-based BIOS, and that they also utilize a well-known data structure called a hash file to verify a Dixie code. So when we plugged in the firmware from the Lenovo into our trusty UEFI tool, it automatically found the structure and highlighted where it's also located. The structure is straightforward. It's basically a triple of entries, each of which define the flash address, the size, and the hash over that region. So really straightforward. But the first issue that we found with it was that the list was actually incomplete because it didn't cover all the firmware modules, firmware volumes that are loaded. And as we can see here, actually it didn't cover the specific firmware volume where some Dixie drivers live. So just to test whether this is actually an issue, we basically did the same thing as we did for the POC. We backdoored one of the Dixie drivers to configure the SMM key, and then at runtime we see over here on the left side, this is the TSIG region, and it should be all Fs, but it's not. So some of you might say, hey, I've seen this before, right? And I would say, how can this be? I mean, I reported this just a few months ago, and I haven't published any details on that yet. So you would actually be right, because in 2021, the binarily team found exactly the same issue, but on Intel-based Lenovos, where different firmware volumes with SMM and Dixie codes were simply not protected. But then another thing that really stood out was that the list wasn't quite in the spot that we expected in the firmware. Why? Because we know that the PEI firmware volume lives in the padding area in the very beginning of the firmware image. But the hash file actually is in a different portion. So we know that the PEI firmware volume is verified by the PSP, but the list is someplace completely else, right? So basically what we found was that not only is the list incomplete, but we can also manipulate the list itself. So from all the systems we evaluated, only 2 of them actually had platform secure boot enabled, and the ThinkPad P16S was actually vulnerable to a trivial implementation issue in the trust chain. So moving on to conclusions, we reported over 20 vulnerabilities affecting different parts of the supply chain, ranging from AMD reference code to IBV code and OEM code. And we found that AMD does provide decent features to lock down the platform, but OEMs just simply regularly fail to apply them. And why this is the case, we think that since Intel is well researched, basically all the focus is on Intel, and there is not really any pressure on AMD because it was still unknown territory. And since AMD implements NDAs and all their interesting documentation, it's really difficult to break the cycle as well. So hopefully with this research, we know a little bit more how systems have to be configured. Whoever has an AMD laptop can just take our tool and run it. And if there are any vulnerabilities, at least in basic configuration issues, you would be able to just quickly run the checks and notify the vendor like, hey, look into that. Which leads me to a call of action, where I encourage you to, if you have an AMD-based system, to take our tool and to just give it a spin. It's available on our corporate GitHub repository, and if you find that it has some interesting results, or if you have any questions, just feel free to reach out to us. Okay. Are there any questions?